inference on slope of a least squares regression line. So the idea is we've done lines of best fit, which is a least squares regression line, and now we're going to kind of go back to it and look at how can we do confidence intervals and hypothesis testing with those lines of best fit. Okay, so I'm going to very quickly talk about how to do a confidence interval as well as a hypothesis test with this type of problem. So we're going to jump into the problem and read it first, and then we'll talk about what exactly we're doing here. Okay, what exactly we're doing. So here we go. A sample of 250 men agreed to participate in a study to determine the relationship between waist size and percent body fat. A scatter plot with body fat was on the y-axis and the waist size in inches was used as the x-axis. The computer output is provided below. Okay, so computer output from that scatter plot. What we're going to do in our first part of this is assume the conditions for inference have been met, construct and interpret a 95% confidence interval for the slope of the percent body fat as it relates to waist size. So here's the gist of it. This video, I'm really keeping it very, very limited because this is kind of the scope and as far as really the AP exam goes. In class, we talked about how to fully check conditions here, the full construction of these problems. In this video, let's keep it very, very bare bones and right to the point. So we're going to construct a confidence interval. The idea is this. When we went and did our lines of best fit, our least squares regression line, we're really collecting a sample. We're collecting a sample and, creating a line of best fit, okay? So really we just have a whole bunch of samples here to create lines of best fit. What a confidence interval is doing is, what if I was able to collect the waist size and percent body fat of all men? Not just a sample of 250 men, of all men on this planet, I was able to construct a percent body fat versus their waist size line of best fit. So we've been dealing with sample lines of best fit. They're saying, what if I created for the entire population all of that data and created a line of best fit? Okay, that's what the confidence interval is trying to do. It's trying to pin down and estimate, if I had that information for the entire population, what would the slope of that line be? Okay, so a 95% confidence interval. What we want here is the formula is going to be B1 plus or minus T star times the standard error of B1. Okay, that's our formula. With T, we do need degrees of freedom, which is n minus 2. So what you really need is you just need to know, what is this formula saying and how do I get that information? When we're talking about B1, what we're talking about, because we're doing a confidence interval on the slope. We're doing a confidence interval on the slope. We're going to take the slope plus or minus T star, which we would get from a T table, times the standard error of that slope. Okay, so what I really need is I need to know my slope and the standard error of my slope, and I can put together a confidence interval as long as I have a T table handy. So when you look at your output, it's been a while. We need to know what numbers in here represent my slope and what represent my y-intercept. How it's going to work is the row that is labeled constant, that is the y-intercept row. So all these numbers up here is all about the y-intercept. That's not what we're focusing on. We're focusing on slope, which is the bottom row, the row labeled waist, okay? So these numbers across here are going to be super valuable to us. That is a slope row. Another way to identify is we see one of our variables here. In fact, it's our x variable, our explanatory variable. Waist is listed here, okay? That's a tell-all for it. So what we have here is this first number, 1.71, that is actually B1. That is my slope. The next number here, it says SE of coefficient. That's the standard error of our slope. So this is SE B1. So being able to read that computer output, you can very quickly put together a confidence interval. So let's do that. 1.70 is my slope, plus or minus, let's come back to T star, and my standard error is 0.0743. I'm going to put that in parentheses because I'm going to multiply by t star here. So my degrees of freedom, I'm going to use that to get my t star, and I'm actually not super prepared for this, but we'll talk through what we do to get a t star. So the degrees of freedom is n minus 2. So take our sample size, which is 250. 250 minus 2, which is 248. This specific computer output actually already included it for you, so that's great. What you would do to look this up in a t-table is you're going to go down that left column to try and find your degrees of freedom. Now, 248 is pretty big compared to the t-tables that we got, so we're going to be between 100 and 1,000 degrees of freedom. So we're going to go down the left column to find our degrees of freedom, and then we go across the bottom and look for 95% confidence. 95% confidence, and we need to look at those two numbers, okay? What we want to pick is these are our t-stars. I want to pick the bigger t-star of the two, not the bigger degrees of freedom, whichever one produces the bigger t-star, because again, I'm constructing an interval to try and estimate and pin down that population slope. So when I did this, I did it off camera already. It is 1.984. So when you're stuck between two degrees of freedom, pick the bigger t-star. I would guess for an AP exam, they're probably going to use a degrees of freedom that's much, much smaller that you can definitely look up. This is your confidence interval for that slope. Okay, so we're 95% confident that the true population slope of percent body fat as it relates to waist size is this interval right here. Now you're like, well, that's not really an interval. It is, it's just not computed out. If you really wanted to calculate the full interval, you can do that. You just sit there and figure out 1.97 plus, what did I say, 1.9? 1.70 plus 1.984 times 0.0743. That's going to give you the upper interval. And then you could do 1.7 minus those two things multiplied out as well. And that would get your interval if you want to go that far. But this is that interval put together. You could always take it farther if you wanted to. Okay, so pulling that information from the computer output is very, very crucial. Let's talk about what a hypothesis test would look like here. So it says, assume the conditions for inference have been met. At the 5% significance level, is there significant evidence to suggest waist size has an effect on percent body fat? So the idea here is slightly different. Confidence intervals are all about just trying to pin down that population slope. The hypothesis test is trying to figure out, is it really linear? Okay, is the situation really linear? So we're trying to figure out, is this really a linear relationship, or did your sample just appear like it's really linear? So when we're doing our null and alternative hypothesis here, what we're doing it on is we're doing it on that population slope. What we're going to assume is that population slope is 0, aka this relationship is not linear. Okay, there is no relationship here. It's not linear. What we're going to try and prove is, no, there is a relationship, and it's either that slope's bigger than 0 or smaller than 0. So people are like, well, how do you pick? Are we going for bigger than 0 or smaller than 0? The clue is in your sample slope. The clue is in your sample slope. Our sample slope was positive, so we're going to look for a situation in which we're greater than 0. Okay, greater than 0. So yes, in class we talked about carrying out a full hypothesis test for the slope. Things that we have here is it says assume the conditions for inference have been met. That was set up above as well. So what that basically means is, hey, everything's working together. These formulas that we're going to use, they're good to go and use them. Okay, traditional AP questions, they're going to include that and say, hey, get right to the point. What's the interval? What's the hypothesis test? What's going on here? Okay. So there is a whole formula for this. T equals B1, so my sample slope minus my hypothesized slope, which we're assuming that's like your population slope is 0. This is traditionally 0. And we're going to divide it by the standard error of B1. So we actually have a lot of this information all together, but this problem's even easier than that. If you look up top, in that same row of slope, there is B1. That is my slope. That's my standard error of my slope. So I could definitely take those and plug them in. But if you look here, it says T ratio and probability. This is the T-score for a hypothesis test on that slope. And this is a p-value for that as well. Okay, a p-value for that as well. So here's the deal. The t, we already have it. It's 22.9, and that's just from looking at my t-score up above. My p-value, you just have to be a little bit careful because that p-value is for a two-tailed test. A two-tailed test. And remember, two-tailed tests are when we're not equal to in my alternative. I'm doing a one-tailed test. So what we would have to do is we'd have to take our p-value of it's smaller than 0.001. We'd have to take that and divide by 2. So if I had a more firm p-value here, so maybe someone told me, hey, the p-value is 0.020. That would be the p-value of a two-tailed test. Since we're doing a one-tail, you got to divide it. It's 0.010. Okay, so p-value, t-score, everything there. This is a very abbreviated approach to inference on slope. The idea is, again, is this is the final unit of an AP statistics course. I've gone in much further in depth in class, but this is kind of the bare bones of what do you really need to know as it comes to the AP exam? Because a lot of times the AP exam is going to say, hey, the assumptions are met. Here's the interval. The assumptions are met. Here's the hypothesis test. Do look back at your notes in class so we can look at what those assumptions really are, how to interpret these things, stuff like that. But this is a bare bones approach on inference of slope of a least squares regression line.